Hey, everybody. It's Monday, May 24th. And as you can see here in the aim today, our goal for today's video is to describe the features of a periodic wave. Essentially, what we are doing is we are picking right back up with the conversation that we left off with on Friday. Now, if you remember from last week, we started to talk about waves and we introduced a number of ideas that are going to be extremely relevant for the entire unit. We started off on Thursday by talking about what a wave is and how a wave is generated by vibrations, and that a wave is really just energy that is traveling through space, and that makes it fundamentally different from a particle because it transmits energy without transmitting matter. That, of course, is exactly opposite of a particle, because when a particle transmits energy, it has to carry its mass and thus the matter it is made of along with it. A wave, on the other hand, is just a transmitter of energy alone, because that's really all a wave is. A wave is just energy. Then on Friday, we talked a little bit about features of a periodic wave. We said a wave is periodic, not only when it is generated by vibrations, like all waves are, whether that's a pulse or a periodic wave, but what makes a periodic wave periodic is that it has a period, or in other words, that it is generated from a regularly repeating pattern. Objects vibrating with a regular period. And so we talked about period, and we talked about frequency. We said period is a measurement of the number of seconds per cycle. That frequency is a measurement of the number of cycles per second. And so because those things are opposites, they're inverses of one another. The period is the inverse of the frequency and vice versa. And if you remember in the video on Friday, I showed a list of features of a periodic wave that included period, frequency, amplitude, and wavelength. And so our goal for today's video really is to dig deep into what the definitions of amplitude and wavelength are. So first, we'll talk about amplitude. Now, the definition of amplitude, I would imagine, of course, this depends on which math class you're in, but I would imagine you might have seen a little bit in math. In physics, we're going to put a little bit of a slight different definition on it, but it's the same idea that you talk about in math. The amplitude of a wave is the measurement of the maximum displacement from the equilibrium position experienced by the particles in the medium. Remember, a wave is just energy. And when a wave travels through a medium, which is just the material through which it's traveling, the particles in the medium vibrate up and down and up and down and up and down in this regularly repeating pattern. What the amplitude is it's a measurement of the maximum displacement from the equilibrium position for these particles. And so it's important to realize, because this is, at the end of the day, a measurement of displacement, the maximum displacement from the equilibrium position, this is just measured in meters. And also, extremely important to note here, it is reported as an absolute value. It is just a number. It is the magnitude of the maximum displacement. Both of these ideas are very, very important, but this last one is extremely important as well. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, it's important to realize that, yes, it is true that amplitude is a measurement of the maximum displacement of from the equilibrium position experienced by these particles, but it's really important to take a moment to ask a question, like, what does that mean? If one wave is causing particles in the medium to be displaced by more, well, then what does that really mean? And it's important to realize that amplitude can be used as a measurement of the relative energy possessed by the wave or being transmitted by the wave. It's easy to think about if you really are visualizing what's happening. If we have particles sitting in a medium, and when one wave passes by, the particles move this much, and when another wave passes by, the particles move this much, essentially what that tells us is the second wave that made the particles displace more had more energy. That is, after all, why the particles in the medium experienced a larger displacement. That should make sense to you. If the particles in the medium are displaced more, then that means they have more kinetic energy individually. And the obvious question is, well, where does that kinetic energy come from? It comes from the energy that is possessed by the wave. And so it's important to realize amplitude is a sort of proxy indicator For energy, what I mean by that is measuring the amplitude is not the same thing as measuring the energy. Remember, amplitude is measured in meters. It's a displacement. But the amplitude gives you a sense of how much energy a wave has, especially when you compare the amplitude of a wave to the amplitude of another wave. Now, because amplitude is a measurement of the energy possessed by a wave, we can put that in real terms when it comes to particular types of waves. If you remember when I was giving examples of different types of waves, talking about transverse and longitudinal waves, I said light is an example of a transverse wave. And so if we're talking about the amplitude of a light wave, we really should just take a second to think, well, if one light wave has more energy than another light wave because it has a bigger amplitude, well, how could you tell? And you could tell because that light wave would be brighter than another light wave. It's important to realize in this context, the word intensity is also used quite a bit. If a light wave is brighter than another light wave, we also talk about its intensity being larger. Intensity is another word really for energy. In the case of light, we would be talking about its brightness. Of course, when we also talked about examples of longitudinal waves, we talked about sound as being an example of a longitudinal wave. And if we were talking about the energy of a sound wave, it should make sense to everybody that essentially we're talking about its loudness or how loud it is. And of course, because energy in all contexts really can be described by the word intensity, when we are talking about the loudness of a sound wave, we're talking about its intensity as well. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at a little diagram. All right, so I want you to write this diagram down because I think it is very important. This is a diagram here that shows you the amplitude measurement for a wave. Notice here we see one full cycle of a wave, and we can tell that this is one full cycle of a wave because we have one full peak and one full trough. And as you can see here, they're showing you the peak or the crest up here, and they're showing you the trough down here, and they're saying this measurement from the peak to the equilibrium line is a measurement of the amplitude. Also down here, from the trough to the equilibrium line is a measurement of the amplitude. This would be reported as the same number because it's just the magnitude of the displacement. It's just reported as an absolute value. Red is probably a bad color for that, but it should also be noted when we are talking about the equilibrium position for these particles, we're really talking about just where they started. Essentially here, what we mean is that's this midpoint line. It's always going to be like what we can think of as the zero line. And so when you were talking about trig in your math classes, when you were talking about sine curves, you might have talked about the amplitude of a sine curve. We just mean this measurement from the zero line to the peak. That's all. And really, we're just talking about how high it is above the zero line. The amplitude of the wave is going to be the same as the amplitude of the particles in the medium. If the amplitude of a wave is 5 meters, essentially what that means is when that wave goes through a medium, it's going to make all of the particles in the medium be displaced by that amount, 5 meters. Take a second to pause this video here and draw that diagram in your notes. And when you hit play, we'll move on. All right, so that's really it for amplitude. There's not a whole lot to say. It's a measurement of the maximum displacement of the particles in the medium. It's measured in meters, and it's just an absolute value. Now, there are a lot of nice questions about amplitude on the regents, which I'm going to show you a bunch of questions of at the end that are combined with wavelength. And so we'll save those after we talk about wavelength. Now, as I mentioned here at the top of the video, the two main features of a periodic wave that we want to talk about today are amplitude and wavelength. So let's take a look at wavelength. Wavelength, totally unsurprisingly, is the length of a wave. But it's not just the length of one wave. It's not just the length of the wave in general, I should say. It is the length of one complete cycle of the wave. More specifically, this can be measured between any 2 points in the medium which are experiencing identical displacements, because that ultimately is how you determine one complete cycle. That measurement can be made from peak to peak. That measurement can be made from trough to trough, or that measurement can be made from the zero line to the time, the next time the wave is going to cause the particles to experience zero displacement. The idea here is that there could very well be a situation where you are shown the diagram of a wave, and that wave diagram contains multiple cycles, like this one. It's important to realize if they tell you this distance here is, whatever, X meters, that's not what the wavelength is. The wavelength is the length of one full cycle. And so it is going to be very important for you to be able to determine one full cycle. The fact that we said a wavelength is the measurement of one full cycle sort of makes that obvious, I hope. We also said yesterday to identify a cycle, you need to be able to realize that a cycle has one full peak and one full trough. So notice between these two red dots here on that diagram, there is one full peak and one full trough, making that one full cycle. Now notice we can also measure that from peak to peak. That contains one full peak and one full trough. Notice here we have half a peak. Down here we have one full trough. And over here we have another half a peak, making that one full peak and one full trough. That measurement is a wavelength. Notice we can also go trough to trough, and for the exact same reason, here if I go from here to here, these blue dots on the bottom, I've got my half a trough over here, I've got my full peak up top, and then another half a trough down here, making that one full peak and one full trough. Notice here now, the definition of the period, the frequency, and the wavelength are all dependent on a particular cycle of the wave. Remember, period is the time for one full cycle. Frequency is the measurement of the number of cycles per second. And the wavelength is the length of one full cycle. It's critically important when you look at a diagram for you to be able to identify either how many cycles are shown or just where one full cycle is. Take a second to pause this video here and write that down. And when you hit play, we'll talk about how to calculate wavelength. All right, now the equation for the wavelength here is pretty straightforward, but like all of the equations that we came up with yesterday for period frequency, they're entirely based on the definition. Notice here it says the length of one complete cycle of the wave. So it should make sense to everybody that the equation is going to be based on the total length here, which in this particular diagram is given as x, and the number of individual cycles that you have. Now, the first thing we should say about wavelength is that the symbol for wavelength is really weird. It's a Greek letter. The Greek letter looks like this. It's pronounced lambda. And so whenever we're talking about wavelength, we usually refer to it as lambda. This symbol that's shown here is italicized. The way that most people print it, like when you're writing by hand, is just like this. You kind of put a backslash and then just a little tail right there. Like that, sort of like a mirror image upside down Y, is perfectly fine. I write lambda pretty quickly, and whenever I do that, it's just like this. As long as you write it like that and you make sure it's connected, it's fine. That symbol is pronounced lambda. And like I was just saying before, if we know that one cycle is 5 meters, then the wavelength is 5 meters. But what if we see a 10-meter measurement, and that's 2 cycles? Well, each cycle would be 5 meters also. And so it should make sense here that your wavelength is going to be the length divided by the number of cycles. So in this equation, we have lambda equals L over the number of cycles, where L is the length measured in meters. The number of cycles here is the number of cycles, and that's unitless, of course, like it was yesterday. And lambda is your wavelength, of course, measured in meters. It should make sense here that because wavelength is a length, definitionally, then it's going to be measured in meters. Take a second to pause this video here, write that down. When you hit play, take a look at how to measure the wavelength in more detail. Okay, so I want to be very clear about this wavelength measurement thing one more time. We already said, and you don't need to write this down again because we already did, the wavelength is the length of one complete cycle of a wave. And more specifically, it can be measured between any 2 points in the medium which are experiencing identical displacements. Here's a pretty good example of that. Notice on the top here, this wavelength measurement is being made from peak to peak. It's got a half a peak over here, a full trough in the bottom, and then another half a peak. Notice it's also measured from 0 to 0 over here by this middle line. Now, this part is very important. The 2 points on the wave have to be showing particles in the medium that would be experiencing identical displacements. Here's what I mean. You see how this measurement starts on the right side of the peak? Well, you could say this is a 0 line and this is a 0 line. So isn't the space between those two black dots a wavelength? No, it's not one full cycle. It's got to be made between this 0 line to the right of the peak to this 0 line, which is also to the right of the peak. Notice if we only made it from here, which I'm now labeling A, from let's just say from Z to A, that only contains one full trough, and that's also why it's not one full wavelength. Notice here this measurement is also shown as being from trough to trough, and we could just measure it from any 2 points on the wave that are experiencing identical displacements. So notice here I went up to the second tick mark on the right side of the peak. So if I go to the second tick mark on the right side of the very next peak, that's also going to be one wavelength long. Being able to measure the wavelength of a wave is critically important. So I'd like you to take a second to pause this video here and draw this diagram in your notes. And when you hit play, we'll move on. All right, so just to put these two things together, now you can see here in this diagram, we have one full wavelength measured. We have our amplitude measured. Notice the amplitude is measured from the equilibrium point up to the peak. Of course, it can also be measured from the equilibrium point down to the trough. And then here they are also showing us one full oscillation, and they are saying the frequency is a measurement of the number of oscillations per second. Now, our goal basically for the rest of this video here is going to be to put this stuff to use. First, I'd like to take a look at a calculation example using that wavelength equation that we just developed. Now, this diagram is a little busy, but it's important nonetheless. I'd like you to take a minute to pause this video and actually sketch this diagram in your notes. We'll go ahead and calculate the wavelength for wave C. That would be this wave up here. You can see it's shown by this like solid line dot pattern. I'd like you to go ahead and take a minute to pause this video and sketch that in your notes. And when you hit play, we'll talk about how to calculate the wavelength of that wave. Okay, so as we mentioned here, and I guess I'll just go back to this really quickly, the equation for the wavelength is the length that we're being shown and the number of cycles within that length. So it should be pretty clear to everybody, but I will highlight it here, that the wave that we are talking about looks like this. I've now highlighted it in red. And so the first thing we should say there is that the length we've shown is 1 meter. And so we're going to write that down as our L. Our length here is 1 meter. But that is not the wavelength. And the reason why that's not the wavelength is because for wave C, we have not been shown one full cycle. One full cycle is one full peak and one full trough. That's only one full peak. That means that's a half a cycle that we've been shown for wave C. The number of cycles is 0.5. And we're looking for the wavelength, lambda. So, as we said, lambda is the length over the number of cycles. And so all we have to do is divide those two numbers. Our wavelength here is the length, 1 meter, divided by the number of cycles, 0.5. And remember, when you're dividing by a half, that's really the same thing as multiplying by 2. So our wavelength here is an even 2 meters. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, moving on to the last part of this video here. All I want to do for the rest of this video is do some practice. Here's an example. This is from the Intro to Waves packet, page 7, number 14. It says, which wave diagram has both wavelength, lambda, and amplitude A labeled correctly? Take a second to pause this video here and try to work this out. Not only should you be thinking about what makes the right answer right, but also what makes the wrong answers wrong. And when you hit play, we'll go over it. Okay, so the answer here, the diagram that shows the wavelength and the amplitude labeled correctly is choice 3. Notice the amplitude is being shown as being from the 0 line up to the peak, which is correct. And in this particular diagram here, we see one full cycle of the wave, one full peak and one full trough. Looking at choice 1 does have the amplitude shown correctly, but this wavelength measurement is wrong because that's half a cycle. Notice that's also true down here for choice 2. That's half a cycle. This one is a double whammy because both of these are wrong. That amplitude is incorrect. The amplitude is measured from the equilibrium line to the peak or from the equilibrium line to the trough and not from the peak to the trough. That measurement is actually 2A. Over here, same thing. That measurement is actually 2A, so that makes that one wrong. But this wavelength measurement is correct because we have one full peak and one full trough. I'd like you to take a second to pause this video here and actually sketch all of these diagrams into your notes. Sketch what I wrote down here, 2A, half cycle, half cycle. These things are super important for you to know. And when you hit play, we'll move on. All right, moving on here. Next question. It says a wavelength is the distance between points. Now, obviously, there are only 4 answer choices, but there are many pairs of points that correctly show you a wavelength. I not only want you to think about what the actual answer to this question is, but what the other points are that show you one full wavelength. Take a second to pause this video here and figure that out, and when you hit play, we'll go over it. Okay, so a wavelength includes one full cycle. It is the length of one full cycle. So it is one full peak and one full trough. A to C only includes one full peak. That is wrong. Choice 2 says A to E, which does include one full peak and one full trough. So that is the answer. Looking here, from B to H, that is not even close. Let's ask a question, though. What is B to H? B to H is the amplitude. That's an important thing to realize here. They're trying to trick you, but that's wrong. And then the next one is showing I to D, and that's double the amplitude. Now, as I mentioned, there are very many other pairs of points which show you one full wavelength here. Notice, from C to G, you got one full wavelength. From B to F, you have one full wavelength. Obviously, from A to E, you have one full wavelength. There are a lot of possibilities here. Also, you can say from H to this imaginary point here, J, we would have one full wavelength. Take a second to pause this video here and sketch that in your notes. And when you hit play, we'll move on. All right, another question with the same diagram here. Question is asking how many cycles are shown in the diagram. As I mentioned before, obviously, these are going to be critical for wavelength calculations. So take a second to pause this video here. Try to figure out how many cycles are shown in this diagram. And when you hit play, we'll move on. All right, now here, they're asking us how many cycles are shown in the diagram. So you should realize by now a cycle has one full peak and one full trough. So there we have one full peak and we have one full trough. So up to E, that's one cycle. But over here, we also have another full peak. I hope everybody realizes if one cycle includes one full peak and one full trough, well, then that means one full peak is a half a cycle. That makes the answer here 1.5. It's really important to realize up, down, and back again is one full cycle. It always contains one full peak and one full trough, so that's a really easy way to identify the number of cycles. Take a second to pause this video here and sketch that in your notes. And when you hit play, we'll move on to one final question. All right, the last question for today, I just wanted to show you because I think it's a little tricky. It says here, the diagram below represents a transverse wave traveling to the right through a medium. Point A represents the particle of the medium. And it says here, in which direction will particle A move in the next instant of time? Now, there are a number of ways that you can approach this problem, but what I think is really important to understand is that a wave is energy. And whether you have a peak or a trough approaching a point in the medium, then that will ultimately determine whether that energy is telling the wave to go up, or to go down. That's the basic idea. Now, the first thing is, notice I said up and down. This is a transverse wave. So that means the point is only going to be able to go up or down. Now, there are two ways to approach this problem. The first way is to do it the long way, and the second way is to use a nice little shortcut. And so I'm going to tell you about the shortcut, but I want to tell you about the long way first. It's important to realize by them saying in the next instant of time, the wave is moving. So instead of the wave being here, it's going to be slightly moved over. And that means it's really going to be located in the next instant of time where this red dashed line is. So notice basically this peak is going to be moved over a little bit. This trough is going to be moved over a little bit. And so notice that means if this trough is going to be located where point A is in the next instant of time, then this thing is going to be down. This particle is going to move down. Now, I think this makes a lot of sense if you look at a simulation of this, and so that's what I want to show you here now. This is the simulator we looked at yesterday. We can get a little wave generated here in this particular diagram, and we can get this to look exactly like the picture that we just had looked. And so notice here in this diagram, this point is just below the equilibrium line, and it has a trough approaching it. So we can say this is just below the equilibrium line, and it has a trough approaching it. So we can say we're using this point as our example. We'll say that's about what the problem was telling us. Now notice, because the trough is approaching it, that means in an instant, this trough is going to be here where this point is. And notice, that's going to make it go down. Notice, while this point is only moving up and down, essentially what it does is it rides the wave. When there's a trough approaching, it comes down. When there's a peak approaching, it comes up. And it just rides the wave up and down and up and down. That's the idea. So it's important to realize when you have a point in the situation that our point was in this diagram, this thing has a trough approaching it. And so if we just follow along the points of the waves, you see how I'm like literally tracing the wave diagram and my pen is going down? That's really all you have to do. If you trace the wave diagram the opposite direction of the wave's velocity, then you'll see the direction the point is going to go in next, and the point is going to go down. And that is ultimately our shortcut. So because a trough is approaching this point, and that trough is going to be where that point is located in the next instant of time, that particle is going to go down. Write this down under the heading particle motion, shortcut. To determine the direction of motion of the point, trace the wave in the opposite direction of the velocity and determine whether the point goes up or down. If your pen goes down, the point goes down. If your pen goes up, the point is going to go up. So we'll say pen down, point down, and if the pen goes up, pen up, point up. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody, that is it for today. And really, now that we have covered amplitude, frequency, wavelength, and period, we are all set as far as really fully finishing these wave basics. And we are ready to move on to some more complicated topics like calculating the speed of a wave. All right, everybody, have a good one.